There is a story that once a smart student asked his teacher, what is the speed of time? I'll say what the teacher said by the end of this video. Before I answer that, I have a question for you all. Okay, so let's again take a segment of a blood vessel. Okay, we know as we age, right, these vessels are going to get thicker and thicker and thicker due to fat deposition. Okay, and we would like to quantify like how thick it's going to get or how old someone is getting using sensors. How do we do that? One of the ways to do this is by using what is known as an approximation for the velocity of blood flow within the vessels. Or if we take a small pulse of blood, it's going to move, say, at a velocity c. Okay. Moen's Korteweg, okay, gives an approximation of what this velocity of pulse wave is based on some properties of the blood vessels. Okay, that's what we are going to look at in this video. And the question that you are going to answer is this. Say we have an old person and a young person. The pulse wave corresponding to an old person, the pulse wave corresponding to a young person. Is this pulse wave going to be higher for an old person or is it going to be higher for a young person? What do you think? Okay, so let's try to answer this as precisely as possible. Okay, C is going to depend on four things. Okay, first is E, the modulus of elasticity of the blood vessels. Okay, for say let's take aorta. For normal aorta, this is about 0.8 megapascals. Okay, it depends on the thickness of the blood vessels, which is where the aging comes, as well as of course the value of E. So small d is the thickness of blood vessels. For aorta, let's say it's about 2.3 mm. Capital D is the diameter of the vessel of interest. Again, for an aorta, it's about 25 mm. Guess what rho is? Rho is the density of blood. Okay, and it's about 1050 kilogram per meter cube. I'm going to use 1000. So the pulse wave velocity depends on these four things. Depends on E, depends on the thickness of blood vessels, also depends on the density of blood and the diameter of the blood vessel. The actual relation derived by Moen and Korteweg is ED over rho D, the square root of that. So let's plug in these values and try to find what the pulse wave is. So this is about 8.6 meters per second. Okay, let's say normal pulse wave velocity. Couple of things happen with aging. First thing is, of course, the modulus of the blood vessels is going to change. That usually changes. One of the primary reasons being the thickness of blood vessels change. Let's say 2.3 becomes 2.6. 2.3 becomes 2.6. The modulus kind of doubles. Okay, let's say 1.6 megapascals. The modulus of elasticity per mole percent. Diameter is also known to increase, so I'm going to make it as 30 mm. Density of the blood, I'm going to hold it constant. Okay, so let's plug in these values and try to find what pulse wave for an older person is. Okay, this should be, so I get approximately 11.8 meter per second. So at this stage, let's try to answer the question that we raised. Okay, so is pulse wave velocity higher in older people or is it higher in younger people? What we get is that pulse wave velocity is higher in older people. So the correct relationship over here, at least by Moen's Korteweg formula, is that pulse wave velocity is going to be higher. Now let's go verify if these numbers actually make sense by comparing with the available data from literature. Of course, here are two values from one of the papers that I read. Okay, in fact, pulse wave velocity is usually higher in older people. As the blood vessels get thicker, the blood wave velocity becomes faster. Okay, now one can use this to estimate the health of a person or the health of a blood vessels of a person. Can you think of ways to measure this velocity? One of the things is you can use something like, say, Doppler ultrasound and measure what the velocity of the pulse, say, at two different segments in an artery. Say we don't have access to costly equipment like ultrasound. It's also possible to measure pulse waves, say, at arteries that are very close to the skin, say somewhere in the carotid, somewhere over here, brachial or femoral artery. Okay. So it is possible to, in fact, non-invasively measure pulse wave velocity. Couple of things. This is an approximate formula. This does have limitations. One of the major limitations is that we know the largest blood vessel, aorta, is not a straight tube. It's curved, right? So there are wave reflections within the blood vessels. Such features are not captured by this model, so one has to come up with more complex models. First thing. And as far as non-invasive measurements go, there are many measurements that try to answer questions like, okay, if I do yoga every day, is it going to keep my pulse wave velocity close to a young people's velocity? Okay, if you are curious, take a look at it. And finally, the answer to that question that I raised initially is that the teacher just said the speed of time is 1 second per second. Okay, with that, thanks for watching. I'll get back to you with a different video.